Welcome to our second workshop where we'll be talking about the vertical mill, how to use it, a little bit about engineering drawings, what makes a good engineering drawing, how to read them, right? How do you take a piece of paper and turn it into a part? And then some kind of tips and tricks on how to safely operate this equipment. So next slide. Yep, a little bit about safety. Michael.
Yeah.
Okay. A little bit about safety. Machine overview, feeds and speeds, cutting operations, reading engineering drawings, tolerances, design for manufacturing, and then we'll actually get out there and we'll do some dice. Hopefully going to keep this kind of short and sweet, give you guys the overview. The important part about this is safety. Right? These machines are dangerous. They can and they will kill you if you aren't focused, keeping your eye on everything, right, and you're not aware, right? If you're wearing necklaces, right, if you're wearing hoodies like these strings, I go into the shop, you tie them up, all right, or you take them out completely so that they don't get caught in the spindle, right? Because if this gets caught on, the first thing that goes towards the spinning thing with a bunch of sharp blades is your face. It's not what you want, all right? So we'll work on that. Who has sandals on? Who has flip-flops? Who's raw dogging the floor right now? Good. I love that. Open-toed shoes are a bad recipe when you go to dealing with heavy metals, kind of working around the shop, because then you lose a toe. And I like 10 of them, so I prefer to keep mine. So these machines that we use are extremely dangerous, especially if handled improperly. Proper clothing will be worn at all times while in the shop and operating the mill. So
You were there.
Oh yeah. Okay. Closed-toed shoes. Work boots are preferred. If you have steel toes, composite toes, anything kind of a heavier duty work boot, wear those. All right. And I also break them in because boots are really comfortable. No baggy clothes. All right. Like this is a relatively form-fitting sweatshirt. All right. But if I was wearing one that's 3 sizes too big, take it off. Right? Or get a smaller sweatshirt. Again, strings and stuff like this, necklaces, jewelry, bracelets, rings, right? All of those can get caught up in machinery and do significantly more damage to yourself than it will the machine. So any long hair needs to be tied back. So up in a ponytail and a braid is fine. Just keeping that out of where you're going to be working, that is mandatory. So never adjust your stock material or tooling while the machine is in operation. All right, so if you're going down to reach through and say this is mounted on the vise and I have the spindle right here, all right, I could reach over here and try to grab it because my hand's not in the way of the spindle, but you mess up, you move a little bit, you jump, something scares you, you're gonna kind of tear up your hand. Don't do that. Turn the machine off, let it spin down before you get anywhere near that. So stop the spindle first, make adjustments. So, and then be aware of the spindle head at all times and everything around it. All right. So knowing where it's at, knowing how it's going to move, knowing how you're moving it, it's going to be critical because that's going to prevent crashes. That's going to prevent you from cutting into the material that you want, that you don't want to remove, right? So being aware of what your actions are going to result in. So. Machine overview. So this is the Bridgeport mill that we're going to be using. It is a manual mill. Sometimes they will have electronic assist. So where you can press a button, flip a lever, and it moves on a screw with using an electric motor. That isn't as precise as hand control or CNC. It is not CNC. It's just an electric motor. There is no G code. There is no code that you put in there to get it out. It's simply moving it left, moving it right, moving forward, backward, up, and down. All right, but it's nice for planing operations, but I wouldn't recommend using it for everything. So we'll get into a little bit about the machine anatomy here. So the cranks and controls. So the knee control lever is going to position the actual knee, what we call the knee, which is going to be where the workpiece is mounted up and down. All right, so that is your Z axis, so to speak. Used to adjust the height of the XY plane, rides on the knee. It can be brought up or down, and the dial indicator is located on the lever and reads in thousandths of an inch. How many of you guys are familiar with thousandths of inch? Right? It's literally just a thousandth of an inch. It is extremely small. It's very hard to see. You can eyeball it sometimes. And if you can't, get good. Y-axis control, that would be located on the side of, on the front of the machine, and that is going to control your front to back. or your y-axis, right? So how many of you guys know the, I guess, right-hand rule for, you know, electromagnetic fields? Kind of same idea, right? You got your x, your y, and your z planes. All right, same thing applies here. You have your x, your y, and your z. So your y is going to control front to back. Your z is your thumb up and down, and then your x is side to side. So the hand crank control adjusts the position of the work holding in the y-axis, motorized and can be controlled by the black box below the crank. You have to be extraordinarily careful with that, because if you don't adjust your feed rate before you do that, you could easily crash that and destroy your piece and parts of the machine. And destroyed end bits aren't fun, especially when they're embedded in the part that you needed. And then your x-axis control is the exact same thing as your y-axis, except in the x direction. The quill hand feed lever. How many of you guys have used a drill press? Pretty simple, right? You crank it down, bit goes down, you plunge it into your part. That's essentially what that is. You can use the mill as a drill press using this lever. Do not, however, mill parts, plain parts, or do any other sort of milling operation with this. This is what I would do exclusively for drilling operations only. Excellent. So work holding, you have a vise, pretty simple. Screw it down, clamps onto parts. All right. How many of you guys? I'm assuming most of you guys know what a vise is. Pretty easy. Parallel bars. So machinist bars, parallel bars. Are very precisely machined, essentially pieces of metal, and they can help aid in leveling parts, making parts square, as well as tool holding. So say you get your piece here, right? And it sits down below where the actual jaws of the vise are, all right? In this case, you can use parallel bars underneath your piece to raise it up so you can have a nice surface finish and a good tolerance or good distance between the actual work hold piece, against the actual work hold and your piece, so that you don't cause a crash, you don't, start chipping away at the vise. It happens. Just try to avoid it as best as you can. Keep our machines nice, keep everything running nice. So, and then additional work holdings. These actually slot into these linear sort of rails. And you can torque them down. So say you have a larger piece that won't fit in a vise, you could use these additional work holding pieces to help aid in securing your piece. The critical thing is always secure your work piece. Every single time you do it, it has to be secured, and you can't have any sort of movement, any sort of vibration in there. Another great thing, if you're going for precise tolerances, clean off the actual workbed. You can see chips and stuff laying here, all right? Those chips can be between, 1/1000th to 15-30 thousandths of an inch, all right? Which means that every time you clamp your piece down, you have a 30 thousandths intolerance between that, all right? So no matter what, no matter how hard you try, that piece is always going to come out wrong. That's just the nature of working with a dirty machine. Clean your machine before you use it. That will give you success every single time. The next one. So the spindle and the quill. So the quill carries the spindle head and will tell you the level via the digital readout and the ruler on the fence. You can set the minimum height of the quill using the dial. So as you can see here, this up and down linear rail or linear screw, I guess. Not really, kind of. Not really. But this dial will essentially limit your depth of drill. So say you need to go down a 1/4 inch, right, into your workpiece. This will allow you to limit your actual travel so you don't drill, say, 1/2 inch deep. Very helpful, very nice to use in case, once we start talking about the tolerances, and you guys will most likely have to use this when you start drilling the die here. So the quill brake. Turn to lock the height of the quill. While this is engaged, you will not be able to move the quill up or down. Do not force it if it does not move. This is a plastic piece. It is easy to break, and when it breaks, it's a pain in the ass to get off. The spindle brake. Turn this to the side to prevent the spindle from turning. This is essentially your lockout. All right, so it keeps the machine from actually spinning up when you don't want it to. It's very helpful if you don't want someone else coming around when, say, you're taking a break. You need to go away from your workpiece, whether you're drinking water, kind of just need to cool down. And you don't want someone else to come up and start machining or taking your pieces because for whatever reason, So using this, it's also a great safety feature because it keeps the machine from turning on. If you bump the spindle, sorry, if you bump the on switch and your hands are in the workpiece, that's dangerous. Don't do that. Use this as a measure. The quill feed is the auto feed to feed the quill up or down. The only engagement, only engage this when the spindle is off. Very similar to what we'll talk about with the lathes. The gears are not synchronous, and so you can actually damage this by trying to engage it while it's on. Think like trying to slam a car into first gear if it's a manual while the engine's on without using the clutch. Don't grind it till you find it. Doesn't work like that. Awesome. Tooling. So you have your tool changer controller. This is pneumatic, so it sounds kind of like an air ratchet. In loads a new tool into the spindle and out releases the spindle. Pretty simple, 2 buttons. It has to be hooked up to air, which I believe all of those are. However, if you go to press this and you don't hear anything happening, no pneumatics, double check that actual the air hose is going into it and verify that first. If it's not, then it's probably just good. Nothing to do about that. But pneumatic tool changer loosens the collet in the spindle or tightens a new one into it. Make sure that the quill is all the way up so that make sure that you reset your quill before you do this. Kind of just a general rule of thumb is reset everything once you go to do a tool change. If you need your workpiece clamped down, you can leave that. However, everything else should be set to 0, at least in the Z plane. So collets used to hold tools in the mill. Come in various sizes and fit tools snugly. As you can see here, different sizes for the different drill bits or end mills that you will be using. Fit the right collet to the right drill bit or end mill every single time. All right. If you have a loose fitting tool in the collet and it falls out, it spins around and it will shoot out, and it can be actually hazardous. I have seen people get stuck with those. It's kind of like an arrow, honestly. When it shoots out, it's scary. Don't do that. Fit everything nice. Make sure everything is where it should be. And then fit that up into the pneumatic tool holder. And then tools. The main tool we'll use is a solid end mill bit. It's flat faced and comes in a varying number of flutes. And more tools will be outlined later. So we'll get into that. Tooling is a very critical part of machining. It's what you need in order to create either a nice finish or conduct operations safely. Using a drill bit to, if you're using a drill bit in place of a end mill, drill bits are not designed for side-to-side forces. End mills are. If you go and try to use an end mill for drilling, sometimes you can, sometimes you can't. It really depends on the tool. This is kind of a brief overview of a very in-depth process, but it'll get you guys operating safely at least. So, coolant. So cutting fluid and oil. Cutting fluid and oil is if you're using something, say you're drilling one of these holes, all right? You don't necessarily need flood cooling for this. You can do a little dab of cutting fluid, whether it's Tapmatic, Mystic, what is it, Mystic Metal Mover? Is that the other one?
Something like that.
Yeah, that's my favorite, Mystic Metal Mover, or other various ones, and ensure that it's compatible with the material you're using. Don't use aluminum cutting fluid on steel cutting fluid. The different formulas don't have the same cooling properties. So helpful to use for light drilling and milling operations. Get good clean cuts and threads in your parts. And WD-40 also works as a cutting fluid if you have it, although be careful when you do that because WD-40 is flammable. It will catch on fire. So I would not recommend it. If you have it, use cutting fluid. So flood coolant, used for hard materials and deep cuts. It extends the life of your tools and it helps to produce a cleaner cut to use. See the switch right here? Make sure the switch and the LED light is on, and then open the ball valve to the desired rate of coolant. So always shut off when finished. It is messy. You will get wet. You will get flood. You will get coolant on the ground. It sucks. Kind of nothing you can do about that. So that's why most CNC machines that you see are enclosed, because that coolant that you pump and you flood through will get everywhere. We don't have that luxury here, so it's kind of, we just got to rock with it. So your digital readout, this is your saving grace. This is how you actually get tight tolerances. This is how you get good, essentially, measurements. All right, you can do it manually. You don't always need a digital readout. Sometimes digital readouts aren't always accurate, so don't trust it. but it's a good kind of starting point. So it displays the position of each axis in inches down to 0.2 10,000ths of an inch. What's 10,000ths? Not thousands. Yeah.
40,000.
0.2 thousandths? Yeah. Oh, that's cheap. This is used to zero out your mill on your work. So what you'll do is essentially a tool touch off where you will zero your X, Y, and Z axis to whatever your work origin is. Right? This is, we'll kind of talk about that in a little bit, but we'll actually pass these drawings back around. And if you see the dimensions in which they're read out, every single face has a 0, 0. That would be your work origin for that operation. So that is where you'd want to zero out your digital readout in order to get accurate dimensions of what you want. So zero out the mill on your work, and then this display is used in tandem with the engineering drawing for precise machining. There are several other measurement tools that you can use to get more precise readouts, such as a micrometer, calipers, and tape measure in that order of precision. So micrometer is hands down the most precise measurement tool that you can use without getting kind of really expensive. Yeah, like without getting in crazy like that, we don't need that. None of what we will do should ever require it, and if it does, redesign it. Then calipers, real quick, real easy. They can get you down close, plus or minus, like 5,000ths. And then tape measure, that's pretty much, it's slightly better than eyeballing, but you're not going to get any sort of precision with that. But next slide. So changing speeds and direction. So the spindle control, as you can see right down here, is that big gray switch, kind of inconspicuous when you're looking at the machine, but that turns on the spindle. That turns on what your tool is, right? So use to select forward or backward, and changes direction changes based on speed and range. So you can, depending on your tool and your tool shape, you can spin it what you consider backwards. However, there are very few cases in which I have found you will use that. So traditionally just use forward. Most of the tools out there are meant for forward motion, so we'll use that. The spindle speed on the front of the machine, you will see the turtle and the hare. It's kind of slow or fast. You can pick up on that. So crank the handle on the side to select the RPM of the spindle, and only adjust while the spindle is turning. Contrary to what the quill feed rate, this one has to be on while you're using it. It uses a series of belts and pulleys, and that must be moving while you do the adjustment. So it will speed up or slow down depending on how you turn it or what you want, but it must be on at all times. Displays the speed based on high or low speed range, and you will adjust that based on the spindle's range select. Used to select which speed range the mill is set to, like changing gears on a car. Both sides have a positive position, and you may have to jiggle the spindle head to get the gears to seat. So if I'm correct, this one has to be off.
Yep.
Yeah. So this one has to be off when you're doing it. So contrary to the speed select, this one also has to be off. The only thing you will adjust when it's on, it's going to be the speed.
I want to create a new neutral.
Yep. Yeah. A new neutral would suck, and that's expensive to replace. So the next slide. Feeds and speeds. Feeds and speeds are the bread and butter of machining. All right, you can machine anything with pretty much any machine as long as you have your feeds and speeds dialed in, right? Speed refers to the speed and RPM of the spindle, all right? Revolutions per minute, all right? Each material requires a different speed for optimal cutting, so you're not going to cut plastic the same as you would case hardened steel, right? If you try to, it will look really ugly. You will most likely break your tool and destroy whatever stock you're using. The table to the right reports the values of the cutting speed on the surface speed per minute per material for high-speed steel tooling. High-speed steel is the general material in which most tooling is made out of, most end mills, most lathes. Other options, the most common second option would be carbide tooling. And so I believe most of what we have is carbide. out there.
No, it's speed steel.
Really?
Yeah.
Oh, gross.
But there's a note on the bottom
Okay.
of that table there.
So, as you can see on the table, a lot of this stuff, we probably won't be machining, like Inconel, titanium, that sort of thing. But if we do, we need it. Here's the table. Multiply the surface speeds by 2.5 for carbide cutting tools. The great thing about carbide is it's extremely tough, but it's very brittle. It will fracture if you have your feed and speeds wrong. You will destroy bits. Will crack them. It's just not fun.
They're very expensive.
Yeah, they are extremely expensive.
That's why we use tool steel instead, because it's a lot cheaper than brakes.
Yep.
And also, if you break it, probably that, and you can get some value in your product, it's good.
Yeah.
Yep. So,
Or embedded in you.
yep.
Or that.
That sucks too. So feeds refer to that surface feet per minute. Oh,
About the calculation, because this is all given in surface feet per minute, then
Yep.
use the calculation.
okay. So you have your surface feet per minute. And so determine the diameter of your cutting tool in inches, right? So say a 1/2 inch bit, 0.5. Use the following formula to determine the spindle speed for your operation. N is equal to 12V over pi times your diameter. V is your cutting speed in feet per minute, see the table. And then D is your diameter of your cutting tool. And so N will give you that spindle speed. That's what you end up meeting. These slides will be posted online. We will also probably make it just quick little handout, something in the future to reference off of, kind of a machining cheat sheet. So feeds refer to the feed rate of the machine, i.e. how fast your bit moves through the material, and your speeds refer to the actual RPM of the machine. So there are two different types of feed rates: the drill feed rate, rate at which the bit feeds vertically down into your material, and the milling feed rate, the rate at which the tool moves horizontally through your material. You can always run your go back. You can always run your mill feed rate a little slower. Generally speaking, if you run your drill too fast, you will snag. So I would say drilling is probably the more risky operation, just because there's significantly more that can go wrong. So drilling feed rate table to the right shows the recommended feed rates in inches per revolution for the different bit sizes. The final feed rate in inches per minute can be calculated using the formula shown. That's a lot of material. That's a lot of information. I'm not going to read through all of that. However, the linear feed rate for drilling in inches per minute is FD, and that will be your final kind of resultant. N is rotations per minute, and feed rate in inches per revolution. So keep that in mind. There are, when you get into like CNC machining, especially, there are two different sort of methods of measuring feeds, inches per minute and inches per revolution. Sometimes your computer can't necessarily translate both, or you have to set up your operation to either read in inches per minute. Chip loading. So chip load refers to the max depth of cut tool will take per cutting edge. This is a value that will be used to calculate the milling feed rates. So as you can see, the chip load is that simple section right here, and basically how much of a chunk you're taking off per tool. So the chip load chart for recommended feed in inch per tooth, given for several different materials, including all of the fancy ones that we are too broke to afford. Good information nonetheless. So milling feed rate, the milling feed rate in inches per minute is calculated using the spindle speed, the chip load, and the number of teeth of the tool, hashtag kind of number of flutes. Flutes refer to traditional drill bits, 2 flutes, right? If you have a fancy, it's basically how many blades you have spinning, right? You can have anywhere between 1 to 700, depending on how big your spindle is.
The Kraken did.
Yeah, like
It's actually the problem.
there are some absolutely crazy bits out there. We're too broke to afford those, so we're gonna probably run with mostly 2 to 4 flute end mills. So as you can see the formula down here for the milling feed rate, FM, the milling machine feed rate in inches per minute, N is the spindle speed per in revolutions per minute, feed in inch per tooth. That's your chip load from the other table, and then NT, number of teeth on the end mill cutting bit.
And then quick note on the number of flutes that you're using. So typically you use a smaller number of flutes for a softer material. So for aluminum, we use 2 flutes. And for a harder material like steel, you'd use close to four flutes or more. I personally have never used 12 flutes. That would be a little insane for what we're working with, but
Cutting operations, so depth of cut terms. So your radial depth of cut, RDOC, the distance a tool is stepping over into a workpiece, also referred to as step over, cut width, or XY. So as you can see right down here and right down here, as well as the axial depth of cut. So the distance in which the tool engages a workpiece along its center line also refers to a step down or cut depth. Getting those right, if you have too much of a depth of cut, you will break your end mill. If you have too little, your process will take significantly longer than it should, also raising cost. So from an actual machining standpoint, if this were a machine shop, you're taking such a small cut because you're afraid of breaking tools, it will take you significantly longer than if you just broke the tool and then bought a new one. Cutting operations, peripheral milling, so an application in which only a percentage of the tool's cutter diameter is engaging in the part. Say you are contouring a part, right? So you actually have a flat stock that's going around and you're just taking the outside radius and going around the outside over and over again to turn down that kind of product. So overall diameter. Manual machining is recommended 10% DOC on steel and harder materials, 25% recommended for soft materials like aluminum and plastic. Heavy depth is reserved for flood coolant and CNC operations. On a manual mill, you do not have the same freedoms that you do on a CNC mill. That's why we have the Tormach now, because we can do a lot more with it than we would with the manual mill. That being said, using the manual mill for most applications is going to be more practical than programming, running through CAM software, and then the setup that goes along with it. Slotting, an application in which the tool's entire cut depth diameter is engaging a part. Slotting removes more material than peripheral cutting. However, it is more risky. The chances of you having the tool fully engaged and breaking it, depending on your feed, is going to be significantly higher. But a shallow DOC on steel and harder materials, medium depth for softer materials like aluminum and plastic. Well, CNC can do whatever it wants because it's CNC and it doesn't care. But only cut where your actual flutes are. If you're running the round part of the actual mill, you're just creating more friction, and friction actually work hardens the material, right? So as you create more heat within that part, that material will actually harden, making it more hard to machine. So that's why we'd like to use coolant for most operations, unless it's impractical to do so. So conventional milling. Conventional milling is where the cutting edge of the tool is rotating away from the direction of the feed. So as you can see, as the feed moves this way, your bit is actually going to be moving counterclockwise to that. So your chip thickness begins at 0 and it increases as you feed into that material. Backlash. Manual milling machines have backlash or slot between the lead screws and the nut. So as you go, you'll feel this when you're machining today. But as you turn the dial, you'll probably get about generally it's like 5 to 10 degrees on those machines. It's probably more like
a quarter of a turn.
Yeah, it's probably more like 45 to 90. So you will actually feel that as you turn the knob, there's a significant amount of slot before you actually engage. It can throw off your digital readout depending upon how that's set up, which I don't know for those machines. Well, okay, good. But characteristics of conventional milling. The chip width starts from 0 and increases, which causes more heat to diffuse into the workpiece and produces more hardening. Like I mentioned earlier, it creates just more problems for yourself. Make sure you keep that part cool. Tool rubs more at the beginning of the cut, causing faster tool wear and decreases tool life. These tools are actually meant for cutting. They like cutting. They work better when you're doing more cutting. Don't just rub, don't let it kind of sit and smack the material and not tickle the material, because then it actually starts to chip more on your way down. Kind of counterintuitive, but it's better if you're actually cutting. So chips are carried upward by the tooth and fall in front of the cutter, creating the marred finish and recutting of chips. Upwards forces created in the horizontal milling tend to lift the workpiece more. More intricate and expensive work holdings are needed to lessen the lift created. This can also affect tolerances and your end product and the quality of your end product. We have something that looks like crap, we don't want to use it. Climb milling. Climb milling is when the cutter rotates with the feed like a truck tire climbing over terrain. Modern machines compensate for backlash or utilize backlash eliminators, making it much easier to use climb milling without vibration problems. Climb milling typically produces a smoother surface finish. Characteristics of climb milling: chip width starts from maximum and decreases as so heat generated will more likely transfer into the chip. When you're machining, that's what you want. If you see your chips coming out and they look exactly the same color as your stock material, most of that heat is actually being dispersed into your material, hardening it. We'll get an example on the lathe especially, but when your chips start to come out and they turn a nice blue color, there's a lot of heat in your chips. It's oxidizing more, which shows you that most of that heat is coming out in your chips much better than the other option. Downwards forces in the horizontal mill are created that help hold the workpiece down. It's less complex work holdings are needed when coupled with these forces. You get away with holding it a little less tough, a little less secure, but still ensure that your material is not going to move. If it does, then you're kind of cooked. And stock material, metal, steel, stuff is not cheap. So.
Oh, shut up. Speeds wizard.
Oh, yeah. Well, actually, can you shut up? I haven't used that before.
Yeah, I'll just.
Yeah.
Yeah, so one thing that you can do to calculate all these things for you, and you can trust it pretty reliably, is an app called the Feeds and Speeds Wizard. So you can look this up on your app store, download it on your phone. You just input the material you're cutting, the tool you're using, the number of flutes, the diameter, the length of it, how deep you're planning on cutting. It'll tell you what your maximum spindle speed will be, what your optimal spindle speed will be, what your feed rate should be. All of this really good information to know. It'll remove all the guesswork out of your operation and just really smooth things along. We've used this quite often for either manual milling or setting up our CNC programming to run on Tormach to make sure nothing breaks, nothing gets too hot or chipped or anything like that. It's a very valuable tool that we like to use often.
I'm guilty of not using that tool nearly enough. Sometimes I just send it and pray. That is not an approach I would recommend. I've broken a lot of parts and pieces.
Yeah, maybe use Feed and Speed.
Yep.
Consult the wizard, Chase. Consult the wizard.
Yeah. Most of the time, it's better to actually just do your research beforehand and then figuring it out. So, reading engineering drawings. So you guys all saw the drawings that I passed around. That is an example of a very well documented, very should I say this? A very precise engineering drawing. So the top view of the drawing, right, as you can see here, 2 times 1.7 and then 2 times 8.3 with your work 0 noted there, as well as your diameter of your hole and the depth of your cut. So the measurement origin is listed, dimension, all of the dimensions are listed, and that little arrow that you see pointing down indicates that is the cut depth. So there's a couple different symbols that we'll talk about in a little bit, but and then that circle with the dash through it, that's indicative of diameter. And so just kind of some weird nomenclature. But on the side view of your drawing, the arrow with the note down here, just to note when you see your CAD software, a lot of times it'll just be a note option, and that adds that in there. So in your notes, what you want to do is include special steps, critical information, anything else that you'd like the manufacturer to know or to look out for. In this case, they're asking us to add a chamfer to the part, that'll be 20 thousandths wide at a 45-degree angle, and, TYP stands for typical, which means that takes place around all four, or yes, every single corner. Not necessarily four corners on a cube, but, that'll allow us, that information is pretty standardized throughout most machine shops in America and around the world. So adding that information, is pretty much a universal language. So we'll go to the next one. Awesome. Tolerances. Tolerances are a defined set of measurements in which the manufacturer can produce while still maintaining dimensional accuracy. Chances are, when you cut your part out, start working on it, it's not going to come out exactly as listed in the drawing. That's when tolerances come in. You can have an acceptable amount of swap in your part and still be able to do the job properly. Right? Rarely is it practical to get a part exactly how it was drawn, within tens of thousands to the hundreds of thousands of an inch. In this case, as you can see here, is based off of decimals. So a 1 point decimal will give you one point of tolerance, all the way down to, again, thousandths of an inch. Same with the angles. One significant figure, plus or minus 5 degrees, all the way down to half a degree. That's fine. Two places is the same. I just ripped that off of the actual drawing sheet here. There are examples of zero tolerance machinery, where you use it's called an electronic discharge machine that you, well, is it it's not electronic.
Electronic discharge machine.
In that case, you can get extremely precise parts because it gets down to the thickness of the wire in which you're running the current through. Using that wire, you can actually essentially blast away material instead of actually milling it down and chipping. You'll end up with a much smoother surface and extremely tight fits. So as you can see here, the reason it's going down so slow is because it's actually restricting the air. And air actually can't get out between the gaps between the two parts. So generally not needed in most applications. In most of the applications we're going to be using here, tolerances will be needed, but getting them extremely precise just takes time and burns money. So
This is a very expensive process, so it's usually used in like injection molding things.
yeah, we don't have a use for it currently. If we do, we might get a machine or look into developing our own. They're actually not that hard to make. Yeah. Let's get the next one. So design for manufacturing. When designing a part, consider the way that the part is going to be used. Say you're designing a lever, right? What do you need that lever to be made of, right? How much force is going to be acting upon that lever? Or it's fulcrum. Its angle and its actual lever arm. How much of that is critical to your design, right? Can you 3D print it? Does it need to be made out of steel, aluminum, right? What's the weight of it? So examples: holes to be mounted, epoxy surfaces, threaded holes for bolts, right? When you're doing a bolt pattern, a lot of those need to be fairly precise, because if you have one part that's different, right, like significantly different, think like half an inch off radially, kind of cooked. It's not gonna bolt together. That's how we know. If there are reinforcements needed to your part, say load-bearing assemblies will need to be designed to take the full load under acceleration, right? You have this cube, right? This probably weighs anywhere between 100 grams, 50 grams to 100 grams, give or take, right? If this experiences 60 Gs, it's going to feel a lot heavier under that acceleration. You will need to design your parts to withstand that acceleration. Happens a lot with rockets, right? As we accelerate and we, gain speed, all of those parts are going to be exerting significantly more force than they would under 1 G of acceleration on Earth, right? So I have the example of a 5 kilogram part at 30 Gs will feel like 150 kilograms at 1 G. So all of your parts need to be designed in order to hold that heavier weight at acceleration. So parts must be designed to be realistically manufactured by their respective process. You're not going to print stainless steel on an Ender 3. That's just not going to happen, despite what some people can say you can do. Metal impregnated filaments suck. Just not even worth using. And don't think about putting a 90-degree bend in a blind hole. Another thing is critical dimensions. So critical dimensions are exactly what they sound like. It's what dimensions are needed in order for your part to fit into your assembly or work properly. What your part will rely on to function. It should have 2 to 3 critical dimensions per part. More than that, and you're just pretty much wasting time. You can 90% of the time cut most of those down, unless, again, some freaky assembly that we're working with. I imagine we probably won't run into that, but you never really know. And then critical dimensions should have tight tolerances, 15 to 5 thousandths. If you really need it precise 5 thousandths, although it's going to be extremely hard to achieve that. And so tight tolerances take more time, thus being more expensive and tougher to get right. If your part is out of tolerance, right, you can always remove more material. You can't add it back, right? So if you take off too much material, that entire operation, all that time that you spent milling that part down, useless. Which kind of sucks. Always try to stick on the higher side of your tolerance, all right? Because if you do need to make changes or you do need to remove more material, you have that luxury. With that, I think that's, yeah, you guys have all seen this before. This is the dice sheet that we've handed around. We'll take those over to the shop with us and we'll start kind of tearing metal. Oh, here we are. So game plan when we actually go out there, we're going to start. We're going to start with the vertical bandsaw. We're going to take our stock material and cut it down to size. So cut to between a 16th and an eighth inch oversize. Use Alumicut or WD-40 as cutting fluid. There should be Alumicut out there, so use that. Again, try not to use WD-40 if you can. And then we'll use the Brown & Sharpe vertical mill to face mill of 2 sides. So pick whatever 2 sides you want to actually mill down. We'll use the Brown & Sharpe for that one. And then we'll run.
Not a Brown & Sharpe, actually.
I thought it was, we only have Bridgeport's.
Well, actually, no, there's the one that's Brown & Sharpe.
Bridgeport's better.
The Bridgeport is better, and the one that we actually talked about.
So we'll probably just use the Bridgeport. So we'll face mill 2 sides using a 1-inch 2-flute high-speed steel end mill. We'll run 955 RPM. Generally speaking, when you get feeds and speeds, you're cool to round them off. So like for this case, 955 RPM, probably cool to round it up to 1,000. It's a little easier to get. However, if the part's screaming, tone it down. Right, you can adjust speeds and speeds depending upon the material, how you're running it. Sometimes the case hardens or work hardens, and you kind of need to turn it up or down respectively. So don't be afraid to change it up. Just you kind of have to get a feel for it. And I don't know if we're quite there yet, but machine the surfaces, cut on the bandsaw, mill one side clean, flip the part milled side down into the vise, and then mill that to size. Use anything else. It's kind of fluid. When you technically can use WD-40.
With aluminum, WD-40 is pretty safe to use. With like steel or something like that, that's going to create a lot of heat while you're cutting. You might start a fire. So maybe don't do it then.
Yeah. And so rough cuts can remove up to 0.1 inches per pass. Remove around 0.01 for the finishing pass. Your finishing pass is always the most critical point while you're machining, because it's going to give you that surface finish that you're looking for. It's going to make post-processing a lot easier, and it can really help give you that nice kind of polished mirror finish. We'll then go on to end mill 2 sides using the same 2-flute high-speed steel end mill, same feeds and speeds. Place part in the vise, previously milled surfaces touching the vise jaws. The benefit of using the machine surfaces is that you know they're going to be consistent and hold it accurately with the actual vice jaws. Say you cut a part off the bandsaw, it's going to have a very rough finish. Not all, it won't always end up giving you the most precise level and square. And leveling your part, squaring your part off with the vise is probably the most important step when you go to set up the machine. And securing your part, making sure everything's right, really kind of affects the rest of the part, the rest of the machining process. So we'll go previous milled surfaces touching the vice jaws, end mill on one end, one edge, flip the part and mill the opposite edge and mill to size using WD-40 as cutting fluid. Rough cuts can remove 0.1 inches, finish passes 0.01. We'll do the edge finding using the edge finder. That's a little bit that sticks in there, and it's very small, very thin. Pardon?
The wiggler.
The wiggler. The wiggler. We'll find the X and the Y edges of the part with the edge finder, and then zero the digital readout on the edges. Remember to 0.01 offset from the edge finder. That's based off of the actual diameter of your tool. So your tool cannot work through material. And so to find your actual work zero on your part, you will need to account for the radius of your part, of your tool. So you're using a quarter inch diameter drill bit, right? You're finding your edge. You need to take 1/8 of an inch off of that in order to find where your actual tool is contacting the part and where that part's origin is. And then we'll use the drilling operation on the Bridgeport mill using a 0.2 inch high-speed steel drill bit or centering drill. I would recommend punching because it's a mill. So I would recommend just using a standard 0.2 inch drill bit if that's what we have. If we don't have that and we only have centering bits, it's fortunate, but okay. And then set up the quill stop for consistent depth. Use WD-40 as cutting fluid, and then rotate the dice and repeat for all 6 sides. Reference the workpiece on vice parallels and the repeatable stop. We'll show you how to set that up in a second here. So, and then manual deburring using a file or deburring tool. We'll show you guys what those are. Files are pretty self-explanatory, but and then break all edges and clean up part. So we'll run with that, and then we'll kind of measure things up, and you'll have a cool dice.